Alrighty, folks, so today we're talking about section 4.8, which is all about something called Newton's method. Right? And this method is for this method is for approximating zeros, which, just as a reminder, are sometimes called roots, depending on the function, of functions. Both those cases, it means finding values where the function is equal to 0. Right? And so the process is that first we make a guess, and we call it x naught, right? So it helps if we can have some sort of, if we have a graph or something, and so we know roundabout where the answer might be. And then we have a formula, which is that x sub n plus 1 equals the x that came before minus the function at that point divided by the derivative of the function at that point. So, for instance, x1 would equal x naught minus f of x naught divided by the derivative of f of x naught. X2 would be x1 minus f of x1 over f prime of x1. And so on and so forth. And then we're just going to repeat using that formula to get higher and higher subscripts until xn and xn plus 1 agree for as many decimal points as we want. Right, so we're going to be approximating, so we're going to be getting a decimal that's close to it, and by the time xn and xn plus 1 agree, then we're probably going to, or xn plus 1 is going to be the same as the 0 for that many decimal points. Right, it'll differ later, but for our approximation, we only care to a certain number of decimal points. So let's do some problems. Approximate the largest root of x to the fourth minus 3x cubed minus 15. So when I graphed this, it looked something like this. So this is going to be what we're approximating, right? That's the root of the polynomial. That's the 0 of that function. And I can see that it's somewhere in between 3 and 4. So my guess is going to be 3. Right? I know that that's not actually a root, but it's a nice, easy number that's close by, probably. Now the formula is going to be that x1 equals x naught minus f of x naught all over the derivative, so we need to know what the derivative is, right? So if that equals y prime, this is a polynomial, so it's a bunch of power functions. So we pop everybody's power down to the coefficient, and then we drop it by 1. The 15 disappears. Now, the thing with Newton's method is it involves repeating something over and over again. So I could do this. I could plug this in, right? Get that x1 equals 3 minus 3 to the 4th minus 3 times 3 cubed minus 15 all over 4 times 3 cubed minus 9 times 3 squared. And I could plug that in and I could figure out what number that is, and then I could start it all over again. Or I could be clever and use a computer, because these sorts of methods really lend themselves to a computer. So considering that my other calculator keeps giving me problems, I've tried out a different one. So it's called Desmos calculator. And this one's really nice because I can define a function, right? So f of x. And here, rather than putting the function that's in my problem, right, rather than putting that polynomial, I'm going to put in the thing that I need to keep repeatedly plug stuff into, right? So that looked like x minus the fraction x to the 4th minus 3x cubed minus 15 all over 4x cubed minus 9x squared. So this is the, right, if it was our formula, all of these x's should have n under them, but that's just what we're plugging into this. That's going to be our part in this, right? The other sort of thing about this calculus, I can't do subscripts, so instead of x1, I'm going to have a, and instead of x2, I'm going to have b, and so on. But x1 is going to be equal to the function with our guess plugged in, and we guessed 3. Right? So x2 is going to be our function with x1 plugged in. Right? That's what our formula is telling us to do. x3 is going to be our function with x2 plugged in. x4 is going to be our function with x3 plugged in. Oh, and it looks like I forgot to say how many decimal points we wanted, but I had planned on saying 3. And it looks like we've already gotten, so that I can't actually click and interact with anything on the screen, so you can't see what I'm pointing at. But with x3, which remember is C here, and x4, which is D here, we've already gotten numbers that agree for the first 3 decimal places. So if all we cared about were the first 3 decimal places, we know that's going to be 3.386. So we can go back to here, and we can say that our answer... Okay, so I know that this is going to take a little delay. We're just going to sit here on the screen for a second. All right, hopefully it will have caught up. I'm going to cut out the place where this crashed again. Apparently it's all calculators that my iPad hates. But anyhow, we figured out that our approximation of the root is going to be 3.386 because that's where that's where we agreed to 3 decimal places, right? If we wanted 4 decimal places, we'd need to keep going. But since all we care about is whether the first 3 decimal places were correct, and we had 2 answers in a row, right? x3 was 3.386, and then some stuff. x4 was 3.386, and then some different stuff. That's fine. We only care about the first 3 digits. And since they match, that's going to be where we stop. That's our approximation. Right? So this seems pretty limiting, right, that we're just approximating zeros. But it turns out we can do a couple of other things. The main one being to estimate the intersection of ln x and negative x, right? So that doesn't sound like a function equals 0 problem, but we know that intersection of ln of x and negative x is really asking where are they equal. And if our question is where are they equal, that's the same thing as asking when this is 0, right? We can add x to both sides, and we get that the graphs are going to intersect when ln of x plus x is equal to 0. So to get our guess, we might still want to graph, right? So if I graph, this is ln of x this is negative x. Right, so I can see they're going to intersect right about here, which I know is a little bit less than 1. Right, it's in between 0 and 1 at least. And I can't plug 0 into this function, so my guess is going to be having x naught equaling 1. Right? And, excuse me, the other thing we need is this is going to be our f of x, right? So f of x is equal to ln of x plus x. So we need to find the derivative of f of x. And remember from our rules, that's 1 over x. This is just a linear function, so we just get the slope. So the our thing is going to be that xn plus 1 equals xn minus ln of x plus x over 1 over x plus 1. Now again, we could plug in and do it by hand, and it wouldn't be too hard for this first one, but after we got to this first one, we'd start getting a little bit tricky. But I strongly, strongly, strongly recommend using technology, even if it's going to make my drawing program crash. But let's hop this up here again and see how it works. So again, we need to define our approximating function, and it's always going to be x minus the fraction of f of x, which we need to go and find the function ln of x plus x. So that's the function that we want to be equal to 0 if we want ln of x to be equal to negative x. And down here, we figured out the derivative was 1 over x plus 1. So that's going to be our function, and our x1 is going to be f of our guess, which we said was 1. Right, so like I said, that one's not too bad. x2 is going to be equal to f of x1. All right. x3 is going to be equal to f of x2. Ooh, looking good already. Let's go to 3 decimal places for this one. Well, we've already gotten to 4. So there's actually nothing special about x3 and x4. It just so happens on these 2 examples that that's where they match up, right? So here we actually know that the first 4 decimal places of the answer are going to be 0.5671, right? If we wanted 5 decimal places, we'd have to keep going, right? We'd have to say that this one, whoops, I can't use F again, and I can't use E because that's a special one. So let's skip to G. Right, there we go. If we wanted 5, 6, 7, 8, 9, right? If we want 9 decimal places, we can go all the way out to x1, x2, x3, x4, x5. Right, but if we just want the first 4 decimal places, we know it's going to be 0.5671. Let's see if we're lucky this time. Nope, we're not. So I'm going to let the audio catch up with the video for a little bit. All right. So, all right, hopefully we're back. And I believe we figured out that the first 4 decimal places were going to be 0.5671. So that is going to be, if we plug that into natural log, we should get negative 5.5671 back, right? That's what it means to be at this intersection. Right? And that seems about right, looking at my sketched graph there. Right? So Newton's method itself is for estimating zeros, but there are a couple of different types of problems that you could reword into saying that they are, you just have to come up with a clever function so that when that function is equal to 0, that's the same as the actual question you're asking, right? So it's usable in a wider variety of opportunities than it sounds. Right? So one thing, if you're watching these in order and you haven't read ahead, we have one more section left, and that section is not 5.1, which is the next section in the book, because chapter 5 starts integrals, and integrals are for Calc 2. We're not going to be dealing with them, right? So our last section is actually chapter 8, section 4, and that is all about something called Taylor polynomials. Now, part of that section has to do with integrals, because it comes after chapter 5, which is where Calc 2 students will learn about integrals. But there's plenty in the section that doesn't have to do with integrals. So you don't need to worry about the integral stuff in that chapter. We're just going to be learning about the stuff around it. And that'll be what we talk about next time.